The universe is mostly ghost. There's this invisible thing, dark matter. It shapes every galaxy, but it slips right through our hands. For decades, it's escaped capture. But the hunt is on. You're going to see 25 attempts to catch it, some from labs buried a mile underground, some from telescopes in space. How do you search for something you can't see? You build a machine so quiet it can hear a single particle whisper. This search is a testament to curiosity. What does it take to solve a mystery written into the fabric of reality? We're trying to catch dark matter. It's not just empty space, it's a real substance. It has mass, it exerts gravity, it shapes the universe, but it's perfectly transparent. Light goes right through. Our eyes can't see it. Our telescopes can't see it. We only know it's there by what it does to everything else. Think of an invisible ocean. Galaxies aren't isolated. They're like ships sailing on that ocean. Their motion is shaped by hidden currents. For decades, astronomers watched those ships. They saw something strange. Stars at the outer edges of spiral galaxies were moving too fast. The visible mass, all the stars and gas couldn't hold them. Without unseen gravity, those stars should have flown off into the dark. That was the key observation. Vera Rubin and her colleagues showed there was missing mass. On a cosmic scale, the universe seemed to be made mostly of something we couldn't see. This phantom presence, dark matter, had to be there, holding it together. But if it's matter, what is it made of? That's where theory meets the hunt. Scientists have proposed candidates, each with its own personality, each needing a completely different kind of trap. For years, the leading suspect has been WIMP, weakly interacting massive particles, heavy, sluggish particles. They'd interact only through gravity and the weak nuclear force. They'd be ghostly but substantial, streaming through the Earth by the trillions every second, leaving no trace. Then there's the action, incredibly lightweight. A billionth of an electron's mass. It would behave less like a particle, more like a field, a pervasive, ethereal field. Under the right conditions, that field might flicker, convert into a faint whisper of light we could detect. There are other possibilities too. Sterile neutrinos, heavier cousins to the neutrinos we know, also flooding through us, interacting only through gravity. Why does this matter? You can't build a trap unless you know what you're trying to catch. Every experiment you're about to see is a direct response to a prediction. Is the target heavy and rare? Then you need a massive, ultra-sensitive detector, buried deep underground to shield it from cosmic noise. Is it wispy and wave-like? Then you need a powerful magnetic field to coax it into revealing itself as a tiny flash of light. That idea is everything. The hunt for dark matter isn't a blind search in the dark. It's a series of calculated gambits. Each experiment is a different kind of net, cast into the cosmic ocean, hoping to feel the tug of a phantom we've never seen. The hunt needs a strategy, a plan for something you can't see. The whole global effort really comes down to two philosophies. They work together. The first is direct detection. The idea is simple. Build the quietest room possible, shield it from everything we know, then you wait. You wait for a signal that doesn't belong, the faintest tick from an atom recoiling, because a dark matter particle might strike it. You're trying to feel the phantom's footsteps as it passes through your trap. Then there's the other side, indirect detection. Here you're not trying to catch the particle itself. You're listening for its echoes across the cosmos. The theory says dark matter particles might annihilate each other or decay, and when they do, they could produce other particles we can see, gamma rays, neutrinos, antiprotons. So you point your most powerful telescopes not at stars, at the places dark matter should be densest, the hearts of galaxies, the centers of clusters. You're listening for the sounds of the animal moving in the forest. Instead of trying to touch it, These two approaches form a kind of pincer movement. Arthur B. MacDonald, the Nobel laureate, he's noted this. A true discovery has to be consistent across methods. If a direct detection experiment claims a signal, then astronomers should be able to point to a region of space and see a corresponding excess of gamma rays. If a telescope sees a strange glow from a dwarf galaxy, then a direct detector should in time feel the particles causing it. One method gives you the fingerprint, the other gives you the context. Without both, any signal is just an intriguing maybe. This duality is the framework. It's why we don't put all our hopes into one machine. It's why the hunt happens in deep underground labs and in the vacuum of space at the same time. Every one of the 25 experiments fits into this scheme. They're different nets cast from different boats, but they're all fishing in the same vast, dark ocean. The strength is resilience. If dark matter hides from one kind of search, it may still reveal itself to another. The Sanford Underground Research Facility is in South Dakota. It's a mile underground in an old gold mine. The mountain above it blocks cosmic rays from space. Inside, there's a machine called elusive Zeppelin, LZ. It's built for patience. At its center is 10 tons of liquid xenon. Xenon is a noble gas. It's kept colder than space. The idea is simple. The leading candidate for dark matter is called a WIMP. If it's real, trillions are passing through the tank every second, and very, very rarely one might hit a xenon nucleus. That collision would be faint. It would make two signals, a tiny flash of light first, then it would knock some electrons loose. The machine is designed to catch these whispers. Arrays of photomultiplier tubes watch for single photons. An electric field pulls the freed electrons up, creating a second flash. 2 flashes for one event. That's the signature, but to hear it, you have to eliminate every other sound. The xenon vessel sits inside a tank of ultra-pure water that blocks radioactivity from the rock, and the mountain blocks cosmic rays. This is a low background experiment. You create a bubble of stillness in a noisy universe. Dr. Hugh Lippincott said the challenge is like listening for a pin drop in a hurricane. You don't just listen harder. You build a room where the hurricane can't reach. LZ is the pinnacle of scale and purity for hunting heavy dark matter particles. It's a monument to an idea. To find a ghost, you first have to learn to be utterly still. Every day it runs, it listens. So far, in that silence, the pin hasn't dropped, but the listening continues. The universe's deepest secrets are worth the wait. This is direct detection at its most ambitious, but then you have to ask, what if the phantom isn't heavy? What if it's impossibly light, but the phantom might be even harder to find? The search changes. It moves to another mountain, in Italy's Gran Sasso Range, where a different experiment is pushing a different idea. Not just size, but total purity. That's Xenon. It's a successor built on decades of work. It uses a huge tank of liquid xenon, kept extremely cold, waiting for a dark matter particle to hit an atom. But the real story isn't the waiting, it's the cleaning, the obsessive cleaning. Imagine trying to hear one perfect note from a distant flute, but you're in a room full of people whispering. The old way was to ask everyone to be quiet. Xenon's way is to remove every other person from the building. It does this with a continuous purification system. It scrubs the xenon of radioactive impurities with impossible precision. One big challenge is an isotope, krypton-85. It occurs naturally in the air in tiny amounts. But here it's noise, so the team made a distillation process so effective it can remove krypton atoms at a level of 1 part in a quadrillion. That's like finding one specific grain of sand on every beach on Earth and taking it out. Elena April founded the Xenon project. She's talked about this journey over 20 years. It's a story of small triumphs. Each generation, Xenon 10, Xenon 100, Xenon 1T, and now Xenon hasn't just been bigger. It's been exponentially cleaner. The background noise, the random ticks from known particles, gets driven down further. This creates a new silence, a window of such clarity that the faintest tremor might finally be seen. Xenon doesn't just wait in the dark, it sculpts the darkness. It carves out a space where only the unknown can speak. That's modern dark matter hunting. Progress is measured in an absence, in the things you remove. It's a testament to ingenuity, this idea that to find a ghost, you first create a vacuum so perfect the ghost has nowhere to hide. The mountain overhead shields it from cosmic rays, but the real shield, the one that matters, is the invisible wall of purity around every atom in that tank. There's a watchful eye buried even deeper. In the Jinping Mountains in China, the rock overhead is thicker than anywhere else. That's where you'll find the China Jinping Underground Laboratory. It's the deepest underground lab on Earth, and inside it, the Panda X4T experiment keeps its vigil. The name is an acronym, Particle and Astrophysical Xenon. It hints at a dual purpose, to probe the unseen substance of the cosmos and the fundamental nature of particles themselves. Like LZ and Xenon, Panda X uses a massive tank of liquid xenon. It's chilled to a state of perfect stillness. It's a time projection chamber, waiting for the twin flashes that would signal a dark matter collision. But its location is its superpower. The immense weight of the mountain above acts as a shield, a more formidable shield. It blocks out even more of the cosmic noise that plagues detectors closer to the surface. That creates an even quieter room in which to listen. The collaboration behind Panda X has focused intensely on the art of listening itself. They've pioneered improvements in how the machine collects the faintest light. Every photon matters, and they've developed a deeper understanding of the electronic whispers, the whispers that ripple through the xenon after an interaction. It's about refining the instrument's hearing, making sure it can distinguish a true signal from the subtlest background murmur. Professor Jai Xiangdong is a leading scientist on the project. He highlights a crucial point about this global search. Independent verification is everything. If one experiment in one mountain sees a hint of something, it could be a local anomaly. A fluctuation, a whisper mistaken for a word. But if a second experiment in a different mountain on the other side of the world, using similar but independently built technology, hears the same whisper, that is when the world would start to listen. Panda X4T is more than a Chinese experiment. It's a critical node in a worldwide network. Its data provides the essential cross-check. It ensures that no single claim can stand without the rigorous scrutiny of a peer separated by geography but united by purpose. This is the hunt at its best. A unified human mission transcending borders, where every quiet chamber deep in the earth is listening for the same echo from the dark. The hunt changes its tools. In a Canadian mine 2 kilometers down inside Snolab, there's the super CDMS experiment. It doesn't listen with liquid, it uses solid crystals, silicon and germanium. Chilled to a whisper above absolute zero, that's cryogenic detection, looking for the faintest tremor in a frozen world. The principle is distinct. Instead of watching for light in a liquid, they're listening for sound in a solid. A particle strikes one of these ultra-pure crystals. It doesn't just create a flash, it creates a tiny vibration, almost imperceptible, a quantum whisper called a phonon. They cool the detectors to a fraction of a degree above absolute zero. That stills the background thermal jitter. The atoms almost stop moving. In that profound cold, the minuscule vibration from a potential dark matter collision becomes audible. The experiment can also measure the tiny electrical charge, the ionization, if any, that such an interaction might free. This dual signature approach senses both vibration and ionization. It gives a unique fingerprint for identification. Dr. Blas Cabrera spoke about tuning into the universe's quantum noise. Super CDMS is that, an amplifier for the faintest notes in the cosmic background. Its strength is sensitivity to lower mass particles. The heavy, sluggish WIMP that large liquid xenon tanks are built for might pass through a crystal without a noticeable shove. But a lighter, nimbler particle, it could deliver just enough energy to make the crystal lattice ring like a microscopic bell. This expands the search. It's not assuming dark matter is one thing. It's preparing for the possibility it could be something else entirely, something lighter and more elusive. The technological diversity is the point. You don't catch every kind of fish with the same net. If dark matter is a school of minnows, you need a net with a finer weave. Super CDMS provides that weave. It represents a different sensory modality. Where other experiments are like telescopes searching for a faint light, this is like a seismometer. Feeling for the faintest tremor in the fabric of matter itself, it reminds you that to find a phantom, you have to be prepared to listen in every way you know. And then invent new ways to hear. The phantom could be so light it's barely matter. At the University of Washington, the hunt takes a turn. The action dark matter experiment ADMX isn't listening for a collision. It's listening for a song. Its target is the action, a hypothetical particle but not from cosmology. It came from a puzzle in the theory of the strong nuclear force. To solve that, physicists proposed a particle with almost no mass, a billionth of an electron's weight, a wisp, and if actions exist in vast numbers, they could be the dark matter. But how do you detect something that insubstantial? You don't try to catch it, you try to coax it into singing. ADMX uses a powerful superconducting magnet. Inside that magnetic field, theory says an action might convert into a single, faint microwave photon. The experiment is a high-tech radio receiver. It has a resonant cavity, a tuned chamber inside the magnet. The team slowly adjusts the size of this cavity, tuning it across a vast range of possible frequencies. They are searching for one specific note, a single, pure tone of microwave light that would appear from nowhere. Professor Leslie Rosenberg led the project for years. He described the challenge. It's like searching for one specific, weak radio station in a universe filled with the deafening static of all other electromagnetic noise. You have to shield the cavity exquisitely, cool it to near absolute zero to quiet its own thermal noise, and then you scan, frequency by painstaking frequency. This is a hunt defined by precision, not brute force. It shows a truth in this search. Dark matter might not be one thing. The universe's hidden architecture could be built from multiple, different phantoms. So our experiments must be as theoretically creative as the particles they seek. ADMX opens a window into a frontier of possibility, where the dominant substance of the cosmos might be an ethereal field, humming a tune we are only just learning how to hear. Some experiments are listening underground, others are watching the sky. The Fermi Gamma-Ray Space Telescope is in orbit. It has an instrument called the Large Area Telescope. It's not looking for starlight, it's looking for gamma rays, the most powerful light there is. Fermi LAT is the main instrument for indirect detection. It uses the whole universe as a lab. Its approach is different. It's not trying to catch a dark matter particle. It's looking for its shadow, for what's left after it's destroyed. The idea is where dark matter is very dense, particles might collide and annihilate. Or maybe over billions of years they decay. Both processes would release energy. They'd create other particles, including these high-energy gamma rays. Fermi LAT's job is to map the gamma-ray sky very precisely. It's looking for glows that don't have an explanation. It looks where dark matter should be thickest, the centers of galaxies, our own Milky Way center, and especially the dwarf spheroidal galaxies orbiting it. These are tiny, faint galaxies. They're thought to be almost pure dark matter, very few stars to create background noise. They're considered clean targets. If dark matter annihilates anywhere, it should produce gamma rays from these places. For more than 10 years, Fermi has gathered data. It's made the most detailed high-energy sky map we have. And what has it found? A deep silence. Dr. Julie McEnery, a former project scientist, said Fermi's biggest contribution so far isn't a detection. It's a series of very sensitive non-detections. It hasn't seen the expected spike of gamma rays at specific energies, the spike many models predicted. This absence isn't a failure, it's a powerful result. It works like a cosmic sieve. It rules out entire families of theories. It tells physicists that if dark matter particles are annihilating, they're doing it much more slowly than we thought. Or maybe through processes that don't make the gamma rays we were watching for. This sends theorists back to their work, to refine the models, to imagine new interactions. To think more creatively about what this phantom could be, Fermi LT shows something important. The universe is the ultimate particle collider and the ultimate detector. Operating at scales and energies we can't match on Earth, by patiently watching its experiments unfold across light years, we learn by listening to what isn't there. Every empty spot in its data is another piece of the map. It tells us where the phantom is not, and in a search this vast, knowing where not to look is just as vital as knowing where to look next. The IceCube Neutrino Observatory is down there at the South Pole. It's built into the ice. They drilled holes a mile deep and lowered strings of sensors, over 5,000 of them. It's a grid, a cubic kilometer of the clearest ice on Earth. And that ice isn't just the structure, it's the instrument. It's a dark matter trap, but a different kind. Its main job is catching neutrinos. Those are ghostly particles from cosmic explosions, but it has another purpose. It's an indirect hunter for dark matter. The theory is this: dark matter particles stream through the solar system. Some could get captured by the sun's gravity, trapped in the core, and there, two of them might meet. Annihilate. That violent process wouldn't make light we could see, but it would produce a burst of high-energy neutrinos, and neutrinos, being ghosts, would race straight out of the sun. Unimpeded, they'd travel for 8 minutes directly toward Earth. That's where the ice becomes a camera. When one of these high-energy neutrinos reaches Earth, it might very rarely strike an atom in the deep ice. That collision creates a secondary particle, and as that particle moves through the ice faster than light can move through that ice, it generates a faint blue glow. Cherenkov radiation, a luminous shock wave. The thousands of buried sensors capture that blue flash. By mapping the timing and the intensity of the light across the array, scientists can trace the neutrino's path backward. They can point back through the Earth directly at the Sun. Francis Haltson, the lead scientist, put it a certain way: they use the Earth as a filter. It blocks other cosmic rays, and they use the ice as a camera. The ancient, transparent ice records the universe's faintest signals. This is the multi-messenger idea. One instrument doesn't just listen for one thing. It listens to a whole symphony: neutrinos from exploding stars, hints of exotic physics, and it scans the sun for the telltale neutrinos that would be the indirect signature of dark matter. That specific signal from the sun hasn't appeared yet, but the ice is always watching, a frozen sentinel. It turns a continent of ice into a window. We could try to make the phantom ourselves. Down in the tunnels under the French-Swiss border, there's the Large Hadron Collider at CERN. It takes a completely different approach. It's not waiting for dark matter to drift into a quiet chamber. It's trying to create it. This is the collider frontier. You smash protons together at almost the speed of light. The LHC recreates those unimaginable energies from a fraction of a second after the Big Bang. In that primordial fire, conditions were right for every kind of particle to burst into being. If dark matter particles were forged back then, maybe we can forge them again. For a fleeting instant, the experiments are called ATLAS and CDMS. They're cathedral-scale detectors that surround the collision points. They're built to capture the debris from these microscopic explosions. But there's a profound challenge. If dark matter is truly invisible, if it only interacts through gravity, it would just fly right through the walls of the detector. It would leave no trace, so physicists don't look for the particle itself. They look for its ghostly shadow in the data. After a collision, they account for all the energy and momentum of every particle that is seen. And sometimes there's an imbalance. A significant amount of energy and momentum seems to just vanish. That missing signature is the telltale clue. It suggests something invisible carried it away. As theorist Nima Arkani-Hamed has pointed out, the LHC could absolutely produce dark matter, but recognizing that production in our data requires a new kind of thinking. We're looking for an absence within a storm of information. This turns the whole problem inside out. Instead of building a trap in the dark, we create the most intense light possible. And we search for a specific kind of darkness within it. It probes a fundamental question. What could dark matter be made of at the particle level? Could it be a partner to the Higgs boson? A supersymmetric particle, the LHC's relentless collisions test these high-energy theories. Its role is complementary, but it's crucial. It doesn't listen for a whisper from the cosmos. It shouts into the void of particle physics, hoping the echo that comes back reveals the shape of everything we cannot see. Precision can be a form of power. You have these massive tanks of xenon listening for heavy footsteps, and then you have something quieter, more delicate, tuned to hear a feather's touch. That's DAMIC deep in Snollab. It takes a different path. It uses charge-coupled devices, the same technology in digital cameras, in astronomical telescopes. But these aren't ordinary sensors. They're scientific-grade CCDs, engineered for an almost impossible sensitivity. They are the experiment. The method is one of exquisite patience. Each CCD is a wafer of ultra-pure silicon, cooled to silence its own atomic vibrations. The team takes what are essentially long-exposure photographs in the dark. Not of light, of charge. They're waiting for the faintest disturbance. When a particle interacts in the silicon, it can knock electrons loose. These freed electrons create a tiny, localized cloud of charge. And the CCD can image that cloud, pinpoint its location to a single pixel, measure its size with astounding accuracy. The size of the charge cloud tells you the energy. That allows DAMIC to look for signals so small they'd be lost in the noise of a larger, noisier detector. It makes it a specialist. Other experiments set lower limits on the mass of potential dark matter particles. DAMIC plunges below that floor. It's designed to hunt for candidates with masses smaller than a proton, these hypothetical light dark matter particles. Sometimes called hidden sector particles, they're so light and nimble they deliver only the gentlest nudge to an atomic nucleus, a nudge too soft for most detectors to feel. But in the pristine, pixel-by-pixel watchfulness of a DAMIC CCD, that minuscule ionization signal might just be visible. As researcher Juan Estrada has explained, the project is a beautiful fusion. It takes precision imaging technology developed for staring at the farthest galaxies and turns it inward, to stare at the quantum behavior of a piece of silicon in a pitch-black cave. It leverages the advance of consumer electronics, smaller, cleaner, more precise transistors, and redirects it toward the oldest question in the cosmos. DAMIC proves a point: sheer scale is not the only path to discovery. Sometimes the answer lies not in building a bigger ear, but in crafting a finer one. A detector that can hear the universe breathing. It's a reminder. The tools we use to map the stars can also map the emptiness between them, to listen for the phantom not with a shout but with a whisper. But the phantom might prefer something else. There's another experiment in those same Italian mountains making a different bet. It's called Dark Side 20K, and it's built around liquid argon. It's a direct competitor to the liquid xenon projects, but it has a different personality. Argon is lighter than xenon. its atoms have smaller nuclei. That changes the physics of a collision. A dark matter particle hitting an argon nucleus could produce a different signal, maybe a clearer one, and argon has a superpower xenon doesn't, called pulse shape discrimination. When a particle interacts in liquid argon, it produces a flash of light. The shape of that light pulse, how it rises and falls over a few billionths of a second, is like a fingerprint. The pulse from an electron recoil, which is common background noise, looks different from the pulse of a nuclear recoil, which is what dark matter would cause. This ability to tell signals apart right at the moment of detection is a huge advantage. It's a built-in filter, sifting potential treasure from the noise from the very start. But the team went further for purity. They sourced their argon from deep underground. Professor Cristiano Galbiotti, a leader on the project, calls this underground argon a game changer. Argon in the atmosphere contains a radioactive isotope, Argon-39, created by cosmic rays. That isotope decays and creates background events in the detector. But argon extracted from underground gas wells has been shielded by the Earth for millions of years. It's naturally depleted of that troublesome isotope. So Dark Side 20K begins its search with a material that's already quiet. A 20-ton core of ancient argon, still liquid, waiting for a whisper from the present. That choice points to a deeper truth in this hunt. It's not about finding the one perfect tool. It's about building a complete toolkit. If dark matter interacts a bit more strongly with argon than with xenon, or if its signal is cleaner to read in argon's light, then having this major experiment online is essential. It makes sure the global effort isn't blinded by a single assumption. We're not just building bigger versions of the same machine. We're cultivating a garden of different detectors, each sensitive in its own way, each listening for the same mystery in a different dialect. That diversification is our greatest strength. It means no matter how the phantom chooses to reveal itself, somewhere a machine is waiting, tuned to hear it. Even the quietest lab underground, it's never completely silent. There's always a murmur, from trace radioactivity in the rock, in the materials of the detector itself. The hunt is learning to hear the difference between that noise and the one note you're listening for, and that's where the SABRE experiment comes in. It uses crystals of sodium iodide, so pure they're almost transparent to the signals they're meant to catch. But the real step forward isn't just the crystals. It's the shield around them. SABRE full name tells you the purpose. Sodium iodide with active background rejection. The crystals sit inside a jacket of liquid scintillator. A traditional shield is passive. It just blocks. This liquid jacket is active. It watches. When a particle from outside tries to get in, a stray neutron, a gamma ray from the walls, it has to pass through the liquid first. And when it does, the liquid flashes, a warning light. That flash tells the system the event in the crystal was just background. Tag it, reject it. This active veto creates a zone of clarity right at the heart of the detector. Like a guard who doesn't just stand at the door, but can point and say which guest is causing trouble. But SABRE design has a second layer. It's being built to operate in two identical setups. One in the Gran Sasso lab in Italy, the other in an underground facility in Australia. Two hemispheres to chase a rhythm. The theory is that as Earth orbits the Sun, it moves through the halo of dark matter around our galaxy. For 6 months, we're plowing into that halo head-on. For the other 6, we're catching up from behind. That motion should create a subtle, seasonal modulation in the rate of dark matter particles coming through. The detection rate in June should be slightly higher than in December, a predicted signature, a yearly heartbeat of the dark matter wind. But to measure that tiny change, you have to be sure it's not something mundane. Local humidity, atmospheric pressure, the changing temperature of the rock itself. With twin detectors on opposite sides of the globe, SABRE cancels out those local seasonal effects. If both detectors in Italy and Australia see their rates rise and fall in sync with the Earth's motion through the galaxy and out of sync with their local seasons, that would be extraordinary evidence. Dr. Elena Gardanseri has pointed to this dual hemisphere strategy as a unique advantage. It turns the whole planet into one calibrated instrument. SABRE is a leap in thinking. It's not just a better trap, it's a smarter one that can tell signal from noise not just in space but in time, listening for the rhythm of our motion through an unseen ocean, waiting to hear if the phantom has a pulse. Deep in the French Alps there's a lab, the Sanford Underground Laboratory. It holds a detector, one of extreme purity. It's called EDELWEISS Roman 3. It uses germanium crystals cooled almost to absolute zero. It's listening for the tiny tremor of a dark matter collision. It's a cryogenic hunter like super CDMS, but its real strength is a different kind of clarity. It can tell the difference between the inside of the crystal and its skin. That's a profound challenge in this search, because the surfaces of these ultra-pure detectors, they can still hold tiny traces of radioactive contamination. A decay from an atom on the surface can produce a signal, and to a less discerning instrument, it looks exactly like the nuclear recoil from a dark matter particle deep inside. It's a perfect mimic, a false alarm. EDELWEISS Roman 3 solves this with its design. Its germanium crystals have interleaved electrodes, a complex pattern of electrical fields that maps the charge from an interaction in 3 dimensions. When a particle interacts in the bulk of the crystal, the charge cloud behaves one way. When it interacts on the surface, the electrical signature is different. The detector can see the geography of an event. It can point and say, this happened inside or this happened on the outer edge. This surface rejection, it's more than a technical trick. It's the bedrock of credibility. To claim you've heard the phantom, you first have to prove you're not listening to the rustling of your own clothes. Dr. Julian Billard, a spokesperson, emphasizes this. The path to discovery is paved with knowing everything that is not dark matter. You have to characterize every whisper, every tick, every known particle signature in your detector. You build a complete library of noise, so when a signal arrives that matches none of it, its strangeness is undeniable. EDELWEISS Roman 3 is that meticulous work. It's not just a machine waiting in the dark. It's a machine that has memorized every shade of darkness we already understand. Its quiet vigil is a masterclass in listening. To hear the universe's deepest secret, you first have to learn the sound of everything else. That meticulous listening, it opens a path to something more ambitious. What if you could not just hear the phantom but see where it came from? That's the directional dream. Experiments like the proposed Cygnus network, the DMTPC technology, they aim for that. They want to do dark matter astronomy to map the invisible wind. Their method is a departure. Instead of a massive tank of liquid, they use a chamber. A chamber filled with low-pressure gas like carbon tetrafluoride. When a particle moves through this diffuse cloud, it doesn't just cause a flash, it leaves a trail. A microscopic track of ionization like the vapor trail of a high-altitude jet. With the right sensors, you can image that trail. You can measure its length, its angle. You can reconstruct its path in 3 dimensions. The direction is powerful because of our motion through the galaxy. Our solar system orbits the galactic center, plowing through the dark matter halo. From our perspective, that creates a wind, a stream of particles seeming to come from the direction of Cygnus. If a detector saw a collection of tracks all pointing back toward Cygnus, that would be a revelation. A smoking gun, as physicist Jocelyn Monroe has argued. No known background process on Earth could produce that. Not radioactive decay, not a stray neutron. It would be a clean, consistent pattern from the cosmos. the fingerprint of the galactic dark matter halo itself, these experiments are still prototypes. The tracks are incredibly faint. The gas volumes needed for a full-scale detector are immense, but the vision is transformative. It moves the search from detection to cartography. We wouldn't just be counting ghosts in a room. We'd be charting the currents of the ghostly ocean we sail through. It's the next step to turn a statistical whisper into a pointed arrow. To not just confirm the phantom's existence, but to finally see the direction of its gaze. The hunt can be a form of archaeology. You're searching for evidence, and that search moves from deep underground labs into deep time itself. Some researchers, they look at the Earth not as a shield but as a detector that's been running for 500 million years. That's the idea behind ancient mineral detectors. It targets an exotic candidate, nuclearite dark matter, a hypothetical nugget, ultra-dense, made of strange quark matter. If an object like that passed through the planet, it would leave a permanent scar. A narrow, linear trail of damage right through the crystal structure of a mineral. Scientists like Dr. Sebastian Baum, they propose we look for these scars. In minerals like mica or halite salt crystals that have lain undisturbed for geological ages, deep in stable formations, shielded from all the churn at the surface. The method is to retrieve these ancient samples. Then, in a lab, you etch them with a chemical solution. The etching process, it eats away along the damaged trail. It makes a microscopic tunnel visible under powerful magnification. It's like developing a cosmic photograph, an exposure time of 100 million years. The potential here is staggering. It integrates over an exposure no human experiment could ever match. It turns the planet's crust into a vast, passive array. A silent witness to a cosmic bombardment we never knew was happening. But the challenges are immense. You have to rule out every other process that could make a similar track. A fission fragment from a trace of uranium. The passage of a heavy, normal cosmic ray nucleus sometime in the distant past. Interpretation is everything. It requires a new field, a marriage of particle physics and advanced geology. To read the scars, you first have to understand the entire life story of the rock. This approach is speculative, a true frontier idea, but its power is in its radical simplicity. It suggests the evidence we seek might not require the most advanced machine we can build today. It might be recorded in the oldest libraries on Earth, in the very stones, waiting for us to learn how to read their language. It's a humbling shift. The phantom we chase through galaxies and particle colliders, it may have left its autograph here at home, in the quiet dark of the bedrock, a signature written in crystal, 1 billion years before humans walked the surface. There's a laboratory working high above the Earth. It's mounted on the International Space Station. It's called the Alpha Magnetic Spectrometer, AMS-02. It faces directly into space. It's not a quiet chamber. It's not shielded. It's a collector. It collects cosmic rays. This instrument is the life's work of Samuel Ting, who won a Nobel Prize. It sifts through the rain of high-energy particles that are always hitting our planet. Its main job is to search for antimatter, to measure cosmic rays with a new level of accuracy. But in all that data, there's another possibility, a whisper. The method is indirect, but it's powerful. As AMS-02 counts the particles coming in, it watches the ratios. The balance between matter and antimatter. It hunts for an excess of positrons. Those are the antimatter twins of electrons, or antiprotons. An unexpected surplus at certain energies could be a clue. The theory is that dark matter particles could be colliding, annihilating in the dense halo of our galaxy. They could be the source. They would produce a spray of standard particles, including these positrons and antiprotons. Those would travel through space to the detector. Samuel Ting has always talked about precision, not just counting, measuring their energy, their charge, their origin across a vast range. That meticulousness turns the instrument from a counter into a kind of diagnostician. The data from AMS-02 has shown intriguing patterns, a rise in the positron fraction at high energies. That caught the attention of physicists everywhere, but then the plot thickened. This excess could be from dark matter annihilations, or it could be from more ordinary sources. Like pulsars, the spinning corpses of dead stars, they also blast positrons into the galaxy. That's the enduring challenge of indirect detection. You find a signal, a ripple in the data, then you spend years, decades, ruling out every other possible cause for that ripple. What's beautiful about AMS-02 is its dual purpose. It's a fundamental physics experiment. It probes the nature of matter itself, and it also serves as a sentinel for dark matter. It harvests a continuous stream of information from the most extreme environment we can access. It turns the space station into a platform for cosmic questions. Its presence in orbit is a reminder. The search isn't just in deep places underground. It's also in the silent, sunlit vacuum right outside our atmosphere, where a single, sophisticated eye watches the incoming traffic from the galaxy. It's patiently compiling a ledger of matter and antimatter, and in that ledger, the signature of the universe's missing mass might one day be found, written in the language of particles that should not quite be there. The Argon experiment is out in the Australian outback, away from all the radio noise. Its full name is the Oscillating Resonant Group Axions Search. It's looking for the action, same as ADMX, but it's listening for a different part of its voice. ADMX is tuned for a low note, a bass note. Argon is listening for a higher pitch. It's probing a mass range for actions that's mostly unexplored, a frontier between the ultralight and the heavy. The design uses something called a dielectric haloscope. You have a powerful magnet creating a strong, uniform field. Inside that field, you place a series of precisely machined disks. These dielectric disks, they aren't just shields, they're active components like the tuned plates inside an instrument. The idea is that an action passing through under the magnetic field could convert into a photon. But the disks enhance that conversion. They act as resonators. They stack the effect, making a faint signal potentially loud enough to hear. It's like you're not just listening for a single flute in a concert hall. You've built an acoustic chamber that amplifies that one flute's note above everything else. Dr. Ben McAllister is a lead researcher. He frames Argon's role as a pathfinder. It's a smaller, more agile experiment designed to scout the territory. The goal is to either hear a signal in this higher mass range or by its silence rule it out. That information is priceless. It tells larger, more expensive projects where to focus their resources or where not to waste them. This is how a global search progresses. Not with one machine, but with a coordinated symphony. Scouts and giants, each playing a distinct part. Argon represents a strategic pivot. As the search for heavy WIMP particles gets more challenging, requiring bigger and quieter detectors, the community is expanding the frontier in the opposite direction. The focus is broadening to include lighter, more wave-like candidates, and that requires a new wave of creativity in the lab. It's no longer just about bigger tanks and purer materials. It's about precision electromagnetism, quantum amplification, turning a volume of space into a finely tuned instrument, listening for one specific note in the universe's hidden symphony. There's a place where detection comes down to quantum touch. In Italy, at the Gran Sasso Lab, there's a project called BULLKID. It's not about size, it's about sensitivity. They're building an array of tiny, perfect cubes. Each one is a cryogenic calorimeter made of sapphire or silicon. They're cooled to within 1,000th of a degree above absolute zero. At that point, the thermal jitter of atoms almost stops. The cubes become still, profoundly still. Each one is a pixel in a vast, quiet sensor, and the goal is to feel the faintest warmth. The principle is simple. If a particle hits one of these microscopic cubes, it deposits a tiny amount of energy. That energy becomes a minuscule rise in temperature. maybe a trillionth of a degree. To measure that, each cube has a superconducting sensor, a device whose electrical properties shift dramatically with the slightest temperature change. It's a quantum thermometer, astonishingly precise. This isn't for the heavy, sluggish WIMP from older theories. BULLKID is built for the lightest candidates. Particles so wispy they'd only give the gentlest nudge to an atomic nucleus. A recoil so small it would vanish in the background noise of a conventional detector. Dr. Laura Cardoni and her team are pushing the energy threshold down toward the quantum limit, the realm where the act of measurement itself has to be considered. They're trying to hear the touch of a cosmic feather. The leap here is in multiplexing. You don't build one exquisitely sensitive cube, you build an array of hundreds, maybe thousands, each one an independent ear listening to its own tiny volume of space. That massively increases the chance of a detection, and it lets the experiment distinguish a true signal from a local fluctuation. If one cube chimes, it might be noise, but if a pattern emerges across the array following the predicted behavior of a dark matter wind, that's a different story. BULLKID is a shift in philosophy. It uses the revolutions in nanotechnology and quantum sensing. It turns away from the monolithic tank and toward the distributed swarm. It's a glimpse of a possible future where detectors aren't vast chambers of liquid. They're forests of microscopic, tuned forks, each one waiting in the deep cold and the dark for the universe's lightest phantom to brush against it and ring a bell no one has ever heard. These silent dark matter labs are already up there, orbiting around us, dozens of them. They're these faint, wispy collections of stars called dwarf spheroidal galaxies scattered around the Milky Way. They're like the 18th experiment, a whole network of cosmic targets painted across the sky. But they're nothing like our galaxy. They're ancient and quiet. They burned through their gas a long time ago. Now they're mostly dark matter, held together by its invisible grip, with just a few old stars tracing out the shape. That simplicity is what makes them powerful. They're clean. With little gas and no new stars forming, there are fewer astrophysical engines around, fewer things to produce high-energy particles that could look like a dark matter signal. They offer a clear view, a blank slate where the phantom's signature could be written. The hunt here works in two parts. First, you have to map the dark matter inside these galaxies. And you do that by watching the stars. Astronomers use powerful telescopes, like the Dark Energy Camera in Chile, to measure the precise motions of these ancient suns. Their speeds, their orbits, all dictated by the gravitational pull of the unseen mass holding everything together. By tracking them, scientists can map out the dark matter halo. Its density, its distribution. It's like figuring out the shape of an invisible magnet by watching how iron filings move around it. Then comes the second part. You point a gamma-ray telescope like Fermi LET at these mapped dark matter reservoirs. You look for an excess of gamma rays coming from their cores. The theory is straightforward. Where the dark matter is densest, particles are more likely to collide, to annihilate, and that could produce the telltale glow. So you combine the gravitational map with the gamma-ray scan. It's a powerful test. Does the gamma-ray signal line up with the peaks of the dark matter distribution? If it does, that's a compelling hint. If it doesn't, it rules out another set of possibilities. Professor Alex Dialika-Wagner calls these dwarfs our dark matter laboratories in the sky. They're natural experiments set up by the universe, operating on scales we could never replicate, and the upcoming Vera C. Rubin Observatory is going to transform this work. It's relentless. All-sky survey will find hundreds more of these faint galaxies. It'll expand our catalog of pristine targets dramatically. This vast astronomical census isn't just passive observation. It's an active, strategic campaign. It provides the context for every underground detector, every space-based detector. It tells the particle hunters exactly where to look. What to expect. It bridges that immense gap between the cosmos and the lab. It turns the entire galactic halo into a structured testing ground. We're not just searching the dark. We're learning to read its architecture, star by slow-moving star, waiting for one of these silent laboratories to finally light up. Even the idea of a particle detector can be thought of differently. There's a 19th approach, and it asks a deep question. What if the particle doesn't have to hit the nucleus at all? What if you could sense it by the way it disturbs the quantum state inside a solid crystal? That's the frontier of magnon detectors. It's one of the most futuristic ideas in this whole search. To get it, you have to think about magnetism differently. In a magnetic material, the spins of the electrons are all lined up. They make a collective field, but that alignment isn't fixed, it can wave. Those collective wobbles, those ripples in the magnetic order, are called spin waves. And just like light is made of photons, a spin wave is made of quantized energy packets called magnons. They're the particles of magnetism. So the theory says an incredibly light dark matter particle, one far too wispy to ever bump a nucleus, could still interact. Not by hitting something, but by putting a tiny bit of energy directly into this magnetic lattice. It could create a single magnon, one ripple in the magnetic sea inside a crystal. Then the challenge is hearing that one ripple. Experiments like Spice and Herald are trying this method. They use crystals of a material called yttrium iron garnet. They put these crystals inside ultra-sensitive superconducting cavities, which are like tiny, perfectly tuned microwave rooms. The idea is the energy from that new magnon could be converted, under the right conditions, into a single microwave photon inside the cavity. And with quantum amplifiers, scientists hope to hear that one photon appear out of the quantum noise. Dr. Jonnet Hochberg, a theorist pushing this path, explains its radical potential. This technique could, in principle, detect dark matter particles with masses 1 billion times lighter than what the big Xenon tanks are built to find. It opens a window onto a universe of phantoms so lightweight they were thought impossible to catch. This approach is just starting, a delicate whisper of an idea being tested in a few labs. But its significance is huge. It shows the creative leap happening at the very edge of physics. It expands the definition of a detector from a tank of atoms to the coordinated dance of spins inside a crystal. We're not just building traps anymore. We're making instruments sensitive enough to feel the universe breathing in a new way. The earliest light we can see is a fossil. And we can read it. This is the cosmic microwave background. It's not something you build. It's an experiment the universe ran for us almost 14 billion years ago. We're the detectives showing up at the scene. That ancient glow is the afterimage of the Big Bang, cooled and stretched by the expansion of space into a faint microwave whisper. It fills the entire sky. Satellites like Planck have mapped it exactly. Ground telescopes, the Atacama Cosmology Telescope, the South Pole Telescope, they refine it further. They're not looking for a particle, they're reading a cosmic ledger. The patterns in that radiation are tiny temperature fluctuations, variations of a few millionths of a degree. But those imperfections are everything. They're the seeds all galaxies would grow from, all the structure we see, and the way those seeds are distributed, their size and spacing, tells a precise story. It tells us what the early universe was made of. It reveals the recipe, ordinary atoms, the stuff of stars and planets. That's only about 5%. Dark energy, the force accelerating expansion, is about 70%, and dark matter, that accounts for roughly 25% of the total mass energy of the cosmos. That number isn't a guess from watching galaxies spin. It's a fundamental parameter etched into the first light. It tells us without question how much of this phantom substance exists. But the CMB can tell us more than just the amount. It's a snapshot, a snapshot of the universe when it was just 380,000 years old. That's the moment the hot, dense plasma of particles and light finally cooled enough. Atoms formed, the fog cleared, and light could travel freely for the first time. That light, which we now detect as the CMB, it froze. It froze the conditions of that instant, including the behavior of dark matter. If dark matter particles interacted with each other or with photons back in those first fiery moments, it would have left a subtle imprint on the polarization of this light. The way the light waves are oriented, experiments are hunting for that signature now in the CMB's polarization maps. A detection would be revolutionary. It would tell us not just that dark matter is there, but that it has a personality beyond gravity, that it can communicate in some faint way with everything else. This cosmological probe sets the grand stage. It provides the bedrock facts, the facts every underground lab, every space telescope has to work from. It tells the experimentalists the budget, how much dark matter is out there to find, and it hints at the rules, the properties their machines need to be sensitive to. It's the ultimate cross-check. Any particle candidate a theory proposes, when you plug it into the models of the early universe, it has to reproduce the detail. The exquisite detail of the CMB map we see. If it doesn't, that candidate is ruled out. So a crystal in a mine listens for a direct whisper, a telescope scans for an indirect glow. And this fossilized light from the dawn of time, it provides the rulebook. It's the silent witness, the immutable witness to the phantom's first act. A scientific claim can sit there for decades, unresolved. Back in the late 90s, an experiment in the Gran Sasso Mountains announced something. The DAMIC/LIBRA group said they saw a signal. And this signal pulsed with the seasons. Their sodium iodide crystals picked up a small, rhythmic change. The event rate would rise and fall, peaking in June, dipping in December. For more than 20 years, that pattern has stayed in their data, and it matches what you'd expect if Earth was moving through a halo of dark matter. But then there's the puzzle. No other experiment has seen it, not with different materials, not with different methods. So physics was left with this question. Was DAMA finally seeing the phantom, or was it just some artifact of their own setup, something specific to them? To answer that, you need an independent judge. An experiment built not to find new things, but to test that one specific claim. That judge is Cosine 100. It's in the Yongyong Underground Lab in South Korea. It uses the same detective sodium iodide crystals, but it applies a new level of scrutiny. The crystals are grown from ultra-pure materials to cut down on internal radioactivity. And the whole array is wrapped in an active liquid scintillator Veto, a guard that can spot and reject background particles from the surrounding rock. That creates a cleaner listening environment. The goal is explicit, to either see the same DAMA signal under these better, independent conditions, or to definitively show it's not there. Dr. Hyun-Soo Lee, a spokesperson, put it a certain way. An extraordinary claim needs verification from multiple, independent lines of inquiry. You can't accept a discovery based on one instrument's testimony. No matter how long it's been speaking, Cosine 100 is that process. Its peer review made physical, the check and balance. So far, its initial results haven't confirmed the DAMA signal. That adds weight to the idea the original finding might be from some seasonal effect inside that one experiment, some unaccounted for thing, but the work keeps going. There are plans for even more sensitive follow-ups. This is how you winnow truth from mystery, not always with a flash of discovery. Often it's the patient work of confirmation. The meticulous work to make sure that if the phantom ever does speak clearly, its voice will be heard by everyone. There's a frontier above the clouds. This 20-second experiment doesn't go down into rock. It goes up, it rises. The general antiparticle spectrometer gaps. It's a cosmic ray hunter that takes to the sky. Designed to fly under a high-altitude balloon drifting for weeks over Antarctica. Up there, above most of the atmosphere, it can listen to the rain of particles from space without the air getting in the way. The planet becomes a filter. The balloon becomes a platform for a very specific search. GAPS isn't looking for dark matter directly. It's searching for the rarest fragments dark matter might leave behind. Its target is the antideuterin. Picture the nucleus of a heavy hydrogen atom, but made entirely of antimatter, one antiproton bound to one antineutron. In the standard cosmic ray background, these are vanishingly rare, so difficult to produce through ordinary astrophysics that finding even a handful would be a monumental clue. It would be the unmistakable debris, the smoking gun, from dark matter particles annihilating each other in our galaxy's halo. To catch that signal, GAPS uses a clever technique. An incoming antideuterin enters the detector, slows down, gets captured by a normal atom. That creates an exotic, unstable combination, an atom made of both matter and antimatter. It can't last. In a fleeting instant, it annihilates, and in that annihilation, it emits a unique fingerprint, a cascade of characteristic X-rays and charged particles. The detector's layers are built to recognize that. Professor Chuck Haley leads the project. He frames the challenge, looking for a needle in a cosmic haystack from a balloon. Every component has to be lightweight but incredibly precise. Survive the brutal cold and vacuum of the upper atmosphere, sift through billions of ordinary cosmic ray events to find the one in a billion anomaly. The one that could change everything. This experiment embodies a different kind of ingenuity, its mobility and altitude, the understanding that some signatures of the phantom can only be gathered from the thin, quiet air at the edge of space, where the atmosphere below acts as a shield, and the vastness above offers a direct line to what the galaxy is hiding. Scaling a successful idea demands its own kind of genius. In that same Canadian lab, SNOLAB, there's another Argon giant, Deep 3600. The name tells you what it is. Dark matter experiment using argon pulse shape discrimination with 3.6 tons of liquid argon. It's a different architectural philosophy, but in the same family. Others use complex multi-phase systems. Deep 3600 is elegantly single-phase. The whole volume of liquid argon is both the target and the light-producing medium. Its vessel is a perfect sphere, lined with over 200 light sensors. That spherical geometry isn't just for looks, it's for efficiency. Any flash of light produced inside, no matter where it happens, has a direct, unobstructed path to the sensors. That maximizes light collection. It turns every possible photon into usable data. But the real power, as Dr. Mark Boulay emphasizes, is in the pulse shape. The same principle that guides dark side. When a particle interacts in the argon, the light it produces has a distinct temporal fingerprint. The pulse from an electron recoil, the common background, rises and falls quickly. The pulse from the nuclear recoil you'd expect from dark matter is slower, more drawn out. Deep 3600 has mastered reading these fingerprints in real time with incredible accuracy. That lets it reject over 99.9% of background events right at the source. It creates a data stream of exceptional purity. Building a detector of this size and purity is a monumental engineering challenge. You aren't just filling a bigger tank, you're ensuring that every single component that touches the argon, every seal, every cable, every piece of support material, is made from radio-pure substances. Materials that won't leach their own faint radioactivity into the sensitive volume. The systems that continuously purify the argon, filtering out microscopic contaminants like radioactive radon, have to operate flawlessly for years. Scaling up means every tiny impurity from a smaller experiment becomes a potential storm of noise in a larger one. Dr. Boulay points to this as the hidden work. The decades of materials science and chemical engineering that make the quiet chamber possible, deep 3,600 results have been powerful in their silence. By not seeing the expected signals, it has placed the most stringent limits yet on how strongly a high-mass WIMP could interact with ordinary matter. It has effectively ruled out vast territories on the map of possibility. This work runs in parallel with Dark Side and others. It creates a vibrant ecosystem within the Argon community. There's healthy competition to push sensitivity further, but also deep collaboration, sharing insights on purification, sensor technology, data analysis. This synergy accelerates progress for everyone. It proves the path to discovery isn't a single road built by one group. It's a network of highways, each constructed with different engineering, but all leading toward the same horizon. The phantom may still be hidden, but the landscape where it can hide is being systematically, ruthlessly mapped. And every ton of argon brought to a state of perfect stillness makes that map more complete. The silence from those detectors, it means something. When LZ or Xenon runs another year and finds nothing, that's not a failure. It's mapping. It's drawing a map. This 24th experiment, it's not a lab experiment. It's not in space. It's a theoretical thing built from all these non-detections. Every null result, every empty data plot, it cuts away a huge part of the possible map. It tells physicists with more and more certainty where dark matter cannot be, where it's not allowed to hide. Theorists work inside these limits. They take a detector's sensitivity, what it can rule out, and they turn that into a constraint for their models. If a theory predicts particles that should have appeared in last year's Panda X data, and they didn't, then that theory has a problem. It needs to change. Or it might be dropped. That's the work, the steady, incremental work of science. It's not a flashy discovery, but it's essential. As Mariangela Lisanti at Princeton says, exclusion plots are the landscape. They're the fences, the boundaries that guide the whole search. It's like searching for a lost city in a huge jungle. Early explorers go out in all directions. But as they come back, reporting no ruins in the eastern swamps, no ruins in the northern mountains, the map of the unknown gets smaller. The consensus shifts. Resources and hope start to focus on what's left, the remaining valleys. The global network of dark matter experiments works like that. A quiet result from an argon detector in Canada informs the next xenon detector in South Dakota. No gamma-ray signal from dwarf galaxies tells a team building a magnon detector which frequencies to scan. This collaborative elimination is how the field moves forward. It funnels creativity and engineering toward the best hiding places. It makes each new generation of experiments smarter, more targeted, built on what we've learned doesn't work. The phantom is still elusive, but the room where it can hide gets smaller every year, more precisely defined, with every year of patient, watchful silence. That's how you solve a mystery when you can't see the culprit. You close every door methodically until only one is left. The ambition comes down to one name. Darwin, it's not something we can build right now, but it's the final vision for this whole search. An observatory so large and so quiet it could hear the background hum of the universe. The design uses a multi-ton core of liquid xenon or argon. It takes the technology from LZ and Xenon and scales it up to a staggering new level. But that scale introduces a profound twist. That kind of sensitivity would pick up a signal we already know but can barely hear. The constant, faint patter of neutrinos. From the sun, from supernova, from the cosmos itself, in a detector the size of Darwin, that neutrino chatter becomes the dominant noise, an irreducible background. The experiment would be so sensitive that the universe's known ghosts become the static on the line. So finding dark matter would mean listening for one specific whisper within all that cosmic static. It becomes the ultimate test of discrimination. To hear the phantom, you have to first understand perfectly the song of every other spirit in the room. This is the culmination of everything learned. Decades of work on purification, on shielding, on sensor technology, all aimed at this one machine. The international group planning Darwin sees it as a definitive instrument. Its purpose is binary and it's monumental. It's designed to do one of two things: capture a clear, unambiguous dark matter signal, or sweep the entire classical territory of the WIMP paradigm completely clean. To prove beyond any doubt that the heavy, sluggish particle we've chased for 40 years just isn't there in the form we imagined. And that result, a comprehensive null result of unprecedented reach, would be a different kind of revolution. It would force theorists to abandon a deeply held framework, to imagine something entirely new, something more exotic, perhaps more subtle, more deeply woven into the fabric of reality. Darwin is the embodiment of a search reaching its logical extreme. It's the point where direct detection either succeeds gloriously or completes its map of the void, and then hands the mystery off to a new generation of ideas. It stands on the horizon, a monument to human patience and ingenuity, a machine meant to listen so closely to the dark that it either hears the phantom's breath or confirms with finality that we have to learn to listen in a whole new way. Machines of steel and crystal are silent, but they're never alone. Behind every ton of xenon, every kilometer of ice, there's a community, thousands of people from dozens of countries. They've staked their careers on a question that might not be answered in their lifetimes. That's the human element, the real engine for these 25 experiments. It's a global collaboration. Nothing in the history of science has been quite like it. An engineer in South Dakota calibrating a photomultiplier tube a mile underground. A physicist in Italy analyzing a pulse shape, a pulse that lasted a billionth of a second. A graduate student in China writing code to filter cosmic noise from a signal. Their work is connected by shared data, but it's more than that. It's connected by a shared dream. They operate with radical openness. Results are published for everyone, especially the null results. A finding from the Jinping lab in China gets poured over immediately. Theorists in Europe look at it. Experimentalists in North America look at it. A new analysis technique developed for a balloon experiment over Antarctica gets adapted for a crystal detector in Canada. This international spirit, it's not just a nice idea. It's a necessity. Dark matter doesn't respect borders. To map a phantom that fills the cosmos, you need a perspective that encompasses the whole planet. The search needs every culture, every scientific tradition. It needs the patience to build relationships that last decades, and the humility to let your cherished theory be challenged. Challenged by a colleague on the other side of the world. Dr. Elena April talks about this. She's from the Xenon project. She describes a collaboration that started with a handful of people. It grew into a family of hundreds spanning continents. They celebrate birthdays, they mourn losses, they argue passionately, argue over the meaning of a single data point. This human network, it's an experiment in itself, a test of our species' capacity for sustained cooperative curiosity. We're building detectors. But we're also building a new way of doing science, where competition becomes a race for better sensitivity, not for solitary glory, where a failure in one lab teaches a lesson. A lesson that prevents a mistake in another lab. The shared purpose transcends language, it transcends politics, it creates a space, a rare space of pure common pursuit. The quiet heroism is in the dedication to a process. These scientists may never hear the phantom's whisper. They might spend entire careers perfecting a machine. A machine that only tells the next generation where not to look, and yet they continue because they understand. every limit that's set, every background that's characterized, every technology that's refined, it's a brick. A brick laid in the road, a road that leads, however slowly, toward understanding our place in a universe dominated by shadow. So when you picture these experiments, don't just see the gleaming chambers. Don't just see the circuitry, see the people, the late-night discussions over coffee, the triumphant cheer when a purification system works, the determined silence when it doesn't. This collective endeavor, this worldwide conversation, it's held in the language of data and discovery, and it might be the most beautiful result of all. It proves something. When faced with the universe's greatest mystery, humanity's response isn't to retreat into isolation. It's to come together, to combine our light, however faint it seems, and to point it bravely into the dark. We've turned the whole planet into an instrument, listening with ancient rock, listening with crystals chilled almost to stillness. Scanning from the silent vacuum of space, from deep inside mountains, these 25 experiments, they're all asking the same relentless question. They're not just machines. They're philosophical statements. Each one is a different bet on the nature of reality, a wager that the phantom, whether it's heavy or impossibly light, will choose to show itself in a specific way. Through a flash in xenon, a tremor in germanium, a single microwave photon in a tuned cavity, or a gamma-ray glow from a dwarf galaxy, that diversity is our greatest strength. It means no matter how the universe built its hidden scaffolding, we have a way to try to see it. The dark matter particle is still at large, a specter slipping through our nets. But calling that a failure misunderstands the journey. The search itself has already changed our world. It's driven monumental advances. The art of creating pure silence, scrubbing materials of their faintest radioactivity, that's given us new standards for low background science. Quantum sensors built to hear a magnon's birth now have uses in medicine and computing. Our maps of the cosmos, refined by the need to find dark matter's hiding places, are more detailed than ever. We've learned to see the universe in ways we never imagined, all while looking for something we can't see. In science, a result of nothing is still a result. A null result isn't an empty page. It's a map with a large, clearly marked territory that says the answer is not here. It's the necessary pruning of possibility. It guides new ideas, it forces creativity. It tells theorists to dream bigger, to imagine stranger phantoms, and it tells engineers to build finer, quieter ears. Every limit set by these experiments is a fence post driven into the soil of the unknown, marking the boundary of what we know, showing us exactly where to explore next. The quest continues. Its rhythm is patience and global collaboration. The next chapter could be written by any one of these experiments. A sudden, unambiguous signal in a tank of argon. A patterned wind of tracks in a directional detector. A perfect note from an action heard for the first time. Or maybe the revolutionary discovery comes from the 26th experiment. The one not yet conceived, inspired by everything we've learned from these 25. This search is a testament to our species' most beautiful trait. Our refusal to accept shadows as emptiness, our drive to reach into the dark and learn its shape.